afternoon, and let me start with answering one question that I am sure someone will ask, and that's not related to the talk, but that's related that why is not my photo in the program, and instead of this there is the crow. So first, I use this logo in GitHub, GitLab, so it's basically you recognize my commits, but also I try to run a little bit experiment. In OpenSSL, we have motto that privacy tools should be available for everyone, but that's not enough. You need to push somewhere for your privacy and so on. So I try to somehow convince our marketing team to just not include my photo, not only because of this experiment, but also I would like to confuse AI algorithms to just assign my name to photo and so on. I know it's a little bit silly, but apparently experiment was successful. So thank you, our marketing team. I know they hate me for this. Okay, so back to the topic. As I am now employed by OpenSSL, but this talk will be about cryptsetup and LUKS encryption, and that is completely independent of the OpenSSL. We use OpenSSL, but the project is developed completely independently. And I'm also a researcher. During my PhD studies, I provided some extensions as authenticating encryption for disk and so on. So I will mention two areas. We don't have much time, so I will mention two areas that touch OpenSSL and where we try to push the privacy and the implementation a little bit forward there. So let's start with that. But first, I should, for people that don't understand exactly how this encryption works, just very quick introduction where these two areas I will be talking about. So first, what is LUKS? LUKS is Linux Unified Key Setup. It was actually output of the PhD thesis of Clemens Frohwirth years ago as LUKS1. I started in Milan in 2009, and then we added, as the team, we added some extensions and so on. So today it's LUKS2, but the principle is still the same. The logic is, as you can see on the picture, we have some data. Imagine any storage, cold storage data, so something that is stored when the computer is switched off, that is encrypted to the disk storage, to the sector. So that's the encryption engine. In Linux, it's usually kernel dm-crypt module, so kernel is encrypting that. Then we have key management, that's actually the Linux Unified Key Setup. That has some key slots, I will explain it later. So we have these two distinct areas. So this encryption running symmetric encryption in some mode, and then we have some password management, doing some stuff with key derivation and so on. So these are two areas I will be talking about. dm-crypt, LUKS. What I would like also to mention, we plan to do some experimental alternative backend, not with dm-crypt, but with uBlock. uBlock is userspace block storage interface based on your URING, so asynchronous block device interface. And here is the first part where OpenSSL will be very useful because everything will run in userspace, and for the encryption we will need to use OpenSSL. We support various backends, but OpenSSL is our primary target. So as I mentioned, how it relates to OpenSSL. First area is key management. I would like to present, let's say, success story, how to extend OpenSSL for something you really need. And the second part is data encryption. As I mentioned, we need some this encryption mode, and that is something that is planned for the future. Unfortunately, I don't have time for more things, but I hope that at least this is interesting. What we would like to do in future somehow is even OpenSSL providers for proof of concept work. So first, very quick introduction what the LUKS actually is. First thing is it's about password management. I know that for the last 30 years, people are big corporations saying that passwords will be completely dead, we will replace it with something. Okay, if it's not password, imagine some token from your face recognition that enters the process of the unlocking this. Basically, it's the password, it's something like that. But because you have disk, the disk is encrypted with one key. That's the principle of this encryption, the last sort of encryption, everything is encrypted with one key, but you would like to unlock it with the token, with the password, so you need somehow be able to change password without re-encrypting the whole key. So that's why there is key hierarchy, that's what LUKS is about. and we have so-called key slots. So imagine this is your disk, NVMe, storage, whatever. There is some metadata, there is data. Encrypted data are your data. It's this encryption, so it has no idea what is the data, only it's split in sectors. For the metadata, there are some additional things I will skip, but there are so-called key slots. Each key slot contains encrypted volume key to decrypt the encrypted data. So each key slot, active key slots, contains the same key, but that key is unlocked by password, token, TPM, whatever. Maybe if you use Linux systemd already has that concept of linking to TPM, so they just provide us this, and the rest is the same. Why I mentioned it here? That's the first story here. We run the password through key derivation function, password-based key derivation functions, and it's there not only to convert password to usable key, but it's also there to provide some resistance to a dictionary and brute force attacks. So if you have some good password, but not so perfect, if you have password 1, 2, 3, 4, nothing will help you. But if you have some good password and there is big dictionary, you still would like that dictionary attack will take some time for attacker. So that's why we have key derivation functions. It will iterate for a longer time. So if you know the password, the iteration is only run once, but for attacker, he needs to run for each password there. But that's its problem. At least it was a problem, because PBKDF as password-based key derivation function 2, that's the name of the algorithm, no, not generic, was the only implemented and only allowed algorithms that basically use only iteration, basically it's iterating hash. But with the constant memory footprint and with GPU or some application-specific integration circuits, so some specific hardware, you can speed up you can run very fast and very much parallel computations there. So solution for some projects were to just increase the iteration time, but then it means, for example, you will wait 1 minute for unlocking, and it still will not solve the problem because the GPUs can run millions tries per second. So the same problem was for password hashing. And in 2014, there was a password hashing competition exactly solving this problem. Winner was algorithm Argon2, which is so-called memory hard algorithm. And they have more cost than only the iteration time. There is also physical memory requirement for the derivation. So you will need, for example, 1 gigabyte of memory to run this derivation. If you are unlocking the laptop, no problem, it's allocated. But for the attacker, he needs for each try, he needs to use this physical memory. And it must be physical memory because the trade-off of time will switch it to exponential time or something like that. So you cannot use swap or something like that. So Argon2 was also usable as key derivation, and we decided to use it for LUKS as one of the first projects. And of course, it was not easy, but it was there. But as you probably everyone teach you, you shouldn't implement crypto yourself. You should use cryptographic library. Good, but nobody in a cryptographic library have this algorithm. So I decided, okay, I'm a researcher, let's find some clever student, and some clever and smart student was Čestmír Karina, who ran the bachelor thesis implementing Argon2 for OpenSSL, and we tried to contribute it there. Well, it's a success story. So it's there, it was finally in OpenSSL 3.2. We switched to the library, so it's available for everyone, but the process as independent researcher, not backed by any company at the time that would like to push new algorithm there, it was not so easy. You can see here, work started 2011, thesis were defended 2020, but there was 3 years of discussion on OpenSSL discussion forum on GitHub until we get where we are now. I know the problem was threat, not the algorithm itself. But anyway, I'm not working for OpenSSL Corporation, so I hope we will a little bit improve in that because it was painful. But we were there. So there is a success story. What I would like to say here, you can have impact if you know how to do that. Push some new algorithm to OpenSSL is not easy task, specifically if there are some complicated things like OpenSSL, but it's doable, and it's doable even from the pure PhD student with the help of some master student. So I'm quite happy to present it there as a success story. The next part is this encryption itself. So let me first try to very quickly introduce how it works, and then why we need some new encryption mode and what we plan to do with that. So very simplified. I know it's real oversimplified, but how it works, you have some storage, let's say plain text data, and the storage is split into sectors or in block. In fact, the file system blocks work exactly the same, but we are talking about this encryption, so let's say it's the disk sector. These sectors are completely independent. Even if you don't encrypt data, you can write one sector from one application, second sector is another application, so it's completely independent, and it must stay independent. So you cannot encrypt, for example, ICBC mode as this, because you have no idea what is written in sector, which application have access to sector 1, which to sector, so that is independent. And this encryption is basically that you put only one layer of encryption there, so some symmetric encryption, usually AES or whatever block cipher, in some mode. Most, or I would say all, this encryption system today use XTS mode. That was specifically designed for encryption of cold storage, so specifically for sectors. And if I mean all programs, it's LUKS, but it's also BitLocker, it's also VeraCrypt, but it's also the hardware encryption, for example, Opal. All this use XTS mode. As I will show you, it's a little bit problematic. So that's how it works. Always performance is important in storage, always. In storage is always performance on the first place. That's why XTS mode was specifically designed. What I would like to mention here, if there is one slide, you should remember this is one. Each textbook, cryptography textbook, mentioned that this encryption is so-called length-preserving encryption. The size of the ciphertext must be the size of plaintext, and you cannot use authenticated encryption because it needs some additional data for authenticated tag, whatever. That's not true anymore. NVMe disk today, enterprise disk, already provide something like this. So you have some sector, typically 4 kilobytes, and you can reformat it to 4 kilobytes plus some additional data, and this is processed automatically. So it's only problem of the firmware. If you don't believe me, this is the list of the NVMe list from my testing server, where I have the enterprise drive exactly formatted this way, and it's up to the drive to just run all sectors atomically. The only problem is that it's for enterprise drives, it's not for the common drives in your notebooks and so on, but it's only a question of firmware. Vendors should easily take the firmware functionality there. So I hope they will do it. So my first plan, and I was a part of my PhD thesis, was to somehow push the encryption of this disk encryption to use authenticated mode. What I didn't say, what it means, length preserver encryption will provide confidentiality. You can only open the data with the key, but it doesn't provide integrity protection. If there is some bit flip, it will quietly decrypt the data. You will get garbage, but you have no indication something changed. Authenticated encryption will of course stop the decryption in that case because there is an integrity failure. Very simple reason. So I hope this is the one way where it should go. And if you have that enterprise drive, you can today use dm-crypt and cryptsetup and use it this way. Maybe there are some performance problems, but that's always with new technology. But there is something more. Okay, let's stay with the length preserving encryption with XTS mode. And everyone used that, so there is no problem. Of course, there is problem, and there is big problem. And not only that mode is designed very strange way, that there are some issues, but that's for performance reason, but it was designed for devices years ago, and storage grows. And with today capacity of terabytes or petabytes, there is one slight problem with internal tweaking derivation, and there can be collision. I will not go into details. If you are interested, we provide this paper as overview of these problems as background for discussion with IEEE work group, storage work group, because they already released the new standard for XTS, where they mention, okay, XTS is no longer secure or shouldn't be used on big devices without so-called key scopes. Key scope is basically the size of storage when you have to change key. So now, all current XTS implementations are not aligned to this new requirement, and we'll have to do something with that. So the attack is there. We try to ask them why they selected some constant. I never get a good answer from them. That's another story. I don't want to criticize that. But the fact is that IEEE standard is there already, and it's waiting for some NIST recommendation for the FIPS. But basically, I would say it means that all XTS encryption will need at least some policy changes and so on. And I will not do that. That's the point. I will explain why. So let me first very quick rant for standards and certification. We don't need post-quantum cryptography. We are using symmetric encryption. We have a long enough key. So sorry, we just need better symmetric encryption modes. But really better symmetric encryption modes, or something that solves the existing problem by definition, not by papering over the problem with the key scopes or something like that, and even without any background, because they set some constant that in principle means that you have to change key after 1 terabyte. And when I ask, where you take this probability? Why is this probability not something else? Nobody was able to answer it's from NIST or from IBM. Someone invented this constant that it's not explained. I don't like this way how this standardization works. So basically, that's where we are now. And what is worse, this was already mentioned on previous slides. For example, NIST suggests for password derivation memory hard algorithm, but they don't define any algorithm. So if you need standardization, you have to switch back to PBKDF2 with all the possibility of DEX. There is no way to use Argon 2 in a certified environment. And here I would clearly say it forces you to use less secure systems. I am not saying unsecure, because the security margin is still there. It's pretty big, but definitely after 10 years of real use of Argon 2 with some definition, I know that algorithms have some problems, but definitely at least NIST should allow that. We are not still there. Anyway, end of rant. I think Petr Gutmann will have some comments about standards later in this room, so I will keep it for him. So what's the plan? And that's basically the end of the story here. I will not spend any time in fixing XTS mode for LUKS. We maybe do some recommendation of the disk size and so on. We will focus on investigating new encryption modes, because there is some new research. New research about the double-decker algorithms. By the way, it was initiated by NIST on some workshops, so maybe there will be some encryption modes. Of course, I know it will take years, so maybe 10 years until it's standardized anyway. But I would definitely better invest my time to testing something that will solve the problem by definition of the algorithm than by just fiddling with some key scopes that will only postpone the issue. And here OpenSSL provides a nice playing part with the uBlock alternative interface. We can test it in user space, run performances, try to implement maybe some new modes for performance. It's probably a good topic for some master thesis and so on. And just be prepared. Why should we be prepared? Cold storage is a long-term issue. You would like your encrypted backup to be secure even after decades. So that's why we need to be some kind of an advance. Of course, you have a completely random password, and you will have backups stored in some physical place. Maybe you are safe with what you have today, but that's exactly about the privacy margin. You need to push it forward there. So that's my plan. And I hope that the certification bodies will definitely somehow allow the Argon as the algorithms, and probably work on new encryption mode standardization. And what I really wish that storage vendors will provide us firmware for the common drives with that additional metadata, so we finally can use the authenticating encryption here. If we can use encryption on the file system level or application level, do that, it's better. But if you know the story about encryption of file system in Linux, the only file system that actually tried to do it correctly was Bcache-FS. That was removed from the kernel last week for non-technical reasons. So currently, if someone mentioned encryption of the file system in Linux kernel, it's basically the same encryption as mentioned with XTS mode, just it encrypts only data, not metadata. So the last sort encryption as file level disk sector encryption is still on place. That's all.
Can you please a little bit more explain the problems with sectors like IM5? Thank you.
Sector with what exactly?
With sectors on the disk. You mentioned that only enterprise drives.
Okay, that's additional space for metadata, I mean. This one? Yeah. Okay, so the problem is that if you have a drive, you will have this sector. This sector will usually just atomic unit, half kilobytes or 4 kilobytes. So you have these sectors. What you can do with today's flash storage, so you have a flash chips there, so you are actually not limited by any kilobytes. You can reformat it internally. You can reformat it as you see here. So you will have 4 kilobytes for the data, but also 64 bytes additional metadata space that will be provided for either application on there. So you will reformat the drive with the NVMe. I demonstrated on NVMe, but probably some other disk providers as well. And then it's up to you. You can ignore the 64 bytes and use it as a previous disk, but you can store something there. That something can be authentication tag. So imagine GCM mode. You have a lot of data and additional tag, and you can store it there, and then you can run encryption with integrity protection. Or you can store anything there, nonce, random initialization vector, whatever. It provides you much more background for better encryption than just length preserving encryption where you have no. I hope it answers the question. Thanks.
Any other?
Thank you very much for the talk. You mentioned that NIST with Argon 2, this was not NIST competition, right? So it was a different one.
Yes.
So do you expect that the Argon 2 will be allowed by NIST? It's close to it, or NIST will run own competition?
Let's be politically correct. Yes, the competition, password hashing competition was completely independent of NIST. It was actually a group of experts. They see the problem, the competition. There were also complaints about Argon 2, like it was the competition of mathematical beauty instead of the algorithm. So Argon has some limits, but it's not better. I am engineers. Engineering is about providing a good solution, not the perfect solution. The good solution is Argon. It works. It's proven. Some systems already use that. If you watch VeraCrypt just released beta version that switched to Argon 2 as well. And NIST already mentioned need for use for memory hard algorithm, but they mentioned ballooning. That is, I think, Dan Bonech algorithm, but it was never in any competition, and it was never released any version. So from the practical point of view, Abitcell, they will be forced to do that. There is no real open. But I have no problem to switch to anything else. That there is nothing else. And there is RFC, the document that already specifies Argon 2. So I wish they do that, but I'm not NIST. Maybe I want to mention, thanks to Czech NUKIP, they already suggest using Argon there. So in Czech Republic, we are a little bit better in that. But of course, FIPS is mandated by that.
Yes. Yes.
So yesterday I heard that very nice talk about homomorphic encryption. Do you think it possible or makes sense to use this kind of encryption with cryptsetup?
I'm not sure if homomorphic encryption applies to this encryption. That would be probably something very crazy. I don't know. That's probably just us. I need to think about that. But if you have sector encryption, what operation over that you would like to do with that? The homomorphic encryption about you can operate with ciphertext and do some operation. What operation would you like to do with encrypted these sectors? Maybe I'm missing something, but this is really for completely different topic. I have no idea. Maybe some expert here will know better. Sorry, I have no answer.
Any questions?
Milan, last time I looked up the cryptsetup documentation on using ASGCM for AAD's supported encryption that was flagged as experimental and had some flaws. Can you comment on this? Has this changed in the meantime?
You mean the documentation for cryptsetup?
Yes.
Yeah. I keep the experimental flag there intentionally because we need to rewrite the algorithms. GCM has flaws because they have very small nonce, and if you calculate the storage size and the sector size, we have problem with this noise. I try to solve that yeah, I generate the noise randomly, but we have problem with big size. So we should use some different algorithm, and we need to do new analysis. So from the point of view of stability of the code, it's not experimental. From the security, I think we need some more mathematical view, maybe proof that the application of the encryption mode is correct. So that's why it's there.
So if you say small nonce, you say that you only use the last 32 bits as nonce, and not the full 100.
I can use whatever is fit in that metadata. That's completely configurable, but GCM mode dictates you size of the nonce. I think 96 bits.
Okay.
Implementation in Linux kernel and by definition. So 96 bits. It's not big. We need more.
Typical.
But I would not use GCM. I would use some different authentication, different IAD algorithm there. But it's not implemented maybe somewhere. So that's why it's experimental. If we have hardware that supports it natively, definitely that will be the major priority there. But the enterprise drives are not in your notebooks.
Okay.
Yeah, we are out of time.
I have one clarification for you. So from the certification point of view for the FIPS, XTS, AES, XTS, the key inequality should be the one of the factors that's actually required for FIPS validation. So that's one thing about standardization. I don't know whether LUKS supports that. How do you ensure that the key that you use for AES versus the XTS portion of the transform, are they equal or not? There should be a verification done prior to.
LUKS is used in FIPS certified environment, and the trick is that we don't implement cryptography ourselves. We use a library is that boundary that is certified that are. So either OpenSSL or Linux kernel, both are certified. So that is our alibi.
Okay, thank you. Any other questions? Please thank Milan.